Remember before we mentioned that the B plus tree have one parameter, which is D. The D parameter is very important. Normally, D controls the shape and the structure of the B plus tree. And when we design a B plus tree as an index table, we have to specify the D value, this parameter. And you may wonder how large this D value can be. Remember, this D controls how many kids we can have for each node, right? So if a D parameter is very small, what will it mean? If D is very small, it means each node we can have a very small number of keys, right? Inside it. What will happen? If we have a very small D, given an index table, if we have many records to put in this B plus tree, then the B plus tree will create for us a small D will be very deep, right? If the D is very small, we have to build a very deep B plus tree instead. Then it will have some problems, because if we have a very deep B plus tree, remember before we do the search process, we have to start from the root and go into these leaf nodes. If this B plus tree is very deep, in other words, the process from the root to the records will take lots of time. And how about the D which is very large? If the D is very large, it means this B plus tree will be very flat, right? Because we can contain so many keys in each node. If this D is very large, in other words, the nodes can be very big, right? We have so many pointers pointing to different tuples, and the tree will be in a very shallow structure. It can reduce the time cost. We do this from the root to the tuple process, right? It can save lots of time. However, can we build a very large D? The answer is no, right? Because when we create an index table, we have to store it in a storage space, like in our hard drive. However, if you still remember, for some disk, right, for the hard drive, we have some size for each of the block. Now, for some systems, we have a block size which will be 4K bytes, right? And we have a limitation for the block. Normally, for convenience in accessing the data, we plan to store the node in one single block, right? We don't want to divide one node into several blocks. Instead, it will create some problems. In other words, the maximum size for a node should be smaller than one block, right? And we have a limited size we are now for each of the D. And to store B plus nodes in one single block, in other words, the D size will be limited. The main reason is because if we plan to store the B plus tree, and we have to allocate the space for both the keys and the pointers. Now, for the keys, we can assign a space with 4 bytes. For pointers, we have assigned a space with 8 bytes, right? Remember the D value, right? Given a D value, the maximum key values we are now for each of these nodes will be 2D, right? You still remember the range, right? It's from D to the 2D. In other words, the largest number of key numbers we are now for each node will be 2D, right? And larger number of pointers for each of the nodes will be 2D plus 1, right? Right. Now this one, we have 2D as the maximum key value allowed for the nodes. Inside, the maximum number of keys we have will be 2D, right? And pointers is always larger than these are keys with 1 extra pointer, right? So therefore, the space we can use for storing the B plus tree will be, the maximum space we can use will be 2D times 4, right? It's for storing the keys, plus 2D plus 1 times 8 is for storing the pointers. It should not exceed the block size. It is no greater than the 4K bytes, right? In other words, D value should be no greater than 170. We have a limited size for D value, right? This is a maximum number we can allow for the D value for creating a B plus tree. And normally in the real world application for the B plus tree, normally we don't use the largest number, and we can use a small number instead. So typical order for the B plus tree will be about 100. Remember that in B plus tree we can have some blank entries, and the typical fear factor for the B plus tree will be about the 67%, right? As to the pointers we have for the nodes, the average fan out will be about 133. In other words, we still have some pointers and the key entries which are blank in the B plus tree's nodes. This is very healthy because later we will show you about how to insert delete for the B plus tree. If we have some blank entries there, it can provide us with some flexibility for inserting new tuples into the B plus tree. In other words, this fan out as well as the feed factors, they are very healthy for the B plus tree. And based on these typical numbers, the capacity we can store for the B plus tree if we have a tree with 4 depths, and the maximum number of records we can store in the B plus tree will be about 133 raised to 4. Right? In other words, this B plus tree can refer to the maximum number of about 312 million records. And we can create so many pointers pointing to this number of records for some tuples. If we have a B plus tree with 3 layers, then the maximum pointers we can point into tuples with about 2 million records. Normally, this size should be sufficient for us if we don't have a very large system to run. However, if we have a very large system like the Amazon or Facebook, and this number can still be very small. And they have to build a larger B plus tree instead. If we have a B plus tree, normally we prefer to hold the top levels of the B plus tree in a buffer pool because we have to use these top layers very often and frequently. Remember, each of the search we have to start from the root, right, and going down. In other words, these top levels have to be very fast to access in the search process. And we can store these top levels in the buffer instead. And now we have a level 1, which will be stored in 1 page, about 8K bytes. Level 2 can be stored in 133 pages, about 1 megabytes. And level 3 can be stored in 70,000 pages, over 133 megabytes. So this is about some properties and the information for B plus tree we can use for database systems. You don't have to memorize the numbers. You just need to know how to calculate the maximum numbers as well as how to calculate this node capacity for certain fan out numbers. As well as storage space we can use in the buffer for storing the top levels. If you know how to calculate them, it should be very easy for you to understand these materials, right? Okay, so this is about B plus tree. And in the next class, we will talk about the insertion, deletion, update of the B plus tree in details. Okay, that's it for today. Thanks for your attention.